All right. Let's start off by reviewing what we talked about last class, and then we can bridge into our topic for today. So, last class we talked about two topics. We talked about effective nuclear charge. And effective nuclear charge is the net strength of attraction from the nucleus to the electrons. The reason why we talk about effective nuclear charge is to explain the trend in atomic radius. In any period from left to right, we see that the size of the atoms gets smaller and smaller. The reason for this is because the effective nuclear charge increases from left to right. Right? And we also went over how to calculate effective nuclear charge. Right? Okay. So effective nuclear charge is calculated as the same value for any family. Right? It doesn't matter which column, it's going to be the same. So that value is constant. And yet the size increases when you go down a family. So the reason is not based on effective nuclear charge. It is based on that there's just more energy levels. Nitrogen has 2 energy levels, phosphorus has 3, arsenic has 4, and so on. Okay, so now let's talk a little bit more about sizes. And so we're going to talk about ions to start with. Now, you remember an ion is going to be either positive or negative, right? So positive ions form, when positive ions form, it's because there's a loss of electrons. You can lose 1 electron, you can lose 2, you can lose 3. All right, so the charge should reflect how many electrons were lost. Now, there's a name for positive ions. Positive ions are called cations. And there's a way to remember that. Cations are positive. So that's how you remember that a cation is positive. Okay? So we also have negative ions. Negative ions form by gaining electrons, and those are called anions. Anions are not as fun, but still, you need to be able to get the name straight. Okay? So, not only do you form positive or negative ions, cations or anions, we need to consider what happens to the size when ions form. So, let's first talk about cations. So, when electrons are lost, you have that's not good grammar. There we go. You have fewer electrons, right? You lose an electron, you lose an electron, or you have fewer electrons than you did when you started. So this can do one of two things. So you could be something like sodium, for example, and sodium, which is 1s2, 2s2, 2p6, 3s1. If I asked you how many valence electrons does sodium have, what would you say? Just 1. Remember, the highest energy level is the valence electron? Okay? So, the thing, we identified these terms before. We said valence electrons, and we call these guys the what? The other ones. Core. Yeah, those are the core, right? If an electron is lost, you really can only lose valence electrons. All right, those are the only ones that can be removed. So if I draw a Bohr diagram, all right, so here, energy level 1, energy level 2, energy level 3. If sodium loses an electron, it loses its valence electron. And so this is what happens. You lose the third energy level. So tell me, did it increase or decrease in size? It definitely got smaller, right? So it lost an entire energy level. That's a huge change. Okay, so losing electrons, this might happen. It might lose an entire energy level, and it's definitely going to get smaller. Okay? All right. Here's another example, the other thing that can happen when you lose an electron. So you could be something like, I'll just pick an element, carbon. One S2, 2S2, 2P2. If carbon loses an electron, it becomes 1s2, 2s2, 2p1, and it has a positive charge. Does that make sense? It lost one electron, right? So your SPF notation has one fewer electron. Okay. All right, so here's the thing. Carbon has two energy levels to begin with. By losing one electron, it still has two energy levels, right? So it doesn't lose a level, it still has two, but the difference is when you have fewer electrons, you have fewer repulsions taking place. And if you have fewer repulsions, the electrons don't need to take up as much space as they did. Right? Your parents don't need as big of a house if there's fewer kids living at home. Right? So it downsizes a little bit. So the result is a slightly smaller atom. And it's, it's a kind of a subtle change, but do you guys see that that is smaller? Right? So the key difference is this. With sodium, when you lost an electron, you lost an entire energy level. In the case of carbon, we lost an electron, but we did not lose an energy level. But it still gets a little bit smaller because now you have fewer electrons banging into each other. They don't take up as much room, so it's going to be smaller. Are you guys okay with that? Yeah, question.
But it still has two energy levels, right?
Correct. It still has two energy levels, right? But instead of being 2s2, 2p2, now it's 2s2, 2p1. All right. So that's what happens when cations form, right? When you lose electrons. What happens when electrons are gained? I'm going to find some space to write. You know what? I'm just going to add a page. I'm going to add a page here. Okay. So let's say we have fluorine gains an electron, becomes an anion. Right? So fluorine was 1s2, 2s2, 2p5, and now that we add an electron, 1s2, 2s2, 2p6. Okay, so did we gain an energy level? No. You gained one more electron. So one more electron means more repulsions. So what's going to happen to the size? Yeah, it's going to get bigger. Dramatically bigger? Not really. Just bigger though, okay? More electrons, more repulsions, larger size. Okay, so now we got those fundamentals out there, right? You gain electrons, it's bigger. You lose electrons, it gets smaller. When it loses electrons, it can get smaller, but for one of two reasons. You got to be able to make sure that you're citing the correct reason. The reasons being either it lost an electron, an energy level, or it just lost an electron, which means fewer repulsions, because those are two different reasons. Okay? All right, so now let's talk about comparisons. There's this term, isoelectronic, and the prefix iso means the same, and the electronic is referring to electrons. So isoelectronic means they have the same number of electrons. And this is actually pretty common. This happens a lot. If we look at this example here, we'll start with krypton in the middle. Krypton is atomic number 36. So if it's atomic number 36, that means it has 36 electrons. But if you look at bromine, bromine here has a minus charge. So bromine normally has 35 electrons, but the fact that it has a minus charge means it also has 36 electrons. Selenium is element number 34. But if it's got a minus 2 charge, that means it has gained 2 electrons, and that's how many electrons it has, 36. All right, let's go the other direction. Rubidium is element number 37, but if it's positively charged, it has lost an electron. Okay, so do you guys catch my drift here? These all have the same number of electrons. If they have the same number of electrons, that means they have the same electron configuration. They would all be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p... No, I went too far. They'd all end in 3p6. No, actually, krypton. They would all go to 4p6. They would all end at 4p6. Okay? So, when things all have the same number of electrons, the thing that is different about them is the number of protons. So, calcium, for example. We'll make ourselves a little chart here. All right, so calcium has 20 protons. But because it's positively 2 charged, it has lost 2 electrons, so it's only got 18. Argon has 18 protons, and it has 18 electrons. So in this comparison, I'm comparing two different elements that have the same number of electrons. All right, so whatever is the same between them is a non-issue. It's a non-factor. The real difference here is the number of protons. So if we ask the question, which one of these is smaller? Well, the one that's smaller is the one that's able to attract its electrons more. Which one would that be? The calcium. Calcium's got more protons. So it's going to attract the electrons inward more, making it smaller. Let's stop here. Does that make sense? All right. Same number of protons. Okay. Let's look at the next example. I've got O2 minus and neon. So let's figure out how many protons and electrons there are in each. How many protons in O2 minus? 8. Yeah. You were thinking valence electrons. I got you. So 8 protons. What about neon? 10. Okay. So for electrons, O2 minus, it's got 2 extra electrons. That means it has 10 electrons. And neon has 10 electrons. Okay. So again, the electrons is a non-factor. The question, which one is smaller? Whichever one has more protons is the one that's smaller. So neon. And it's the same reasoning as above. Okay, so what about this one? Iron. How many protons in iron? 26. They're both iron, so they both have 26. But let's count the electrons. So iron with a +2 charge, 24. Okay, now iron with a +3 charge, 23. So the nuclear charge, the number of protons, is constant. So that's a non-factor here. So the difference is the number of electrons. If I'm asking which one of these is larger, how can you explain which one of these is larger based on just that? Yeah, Kate.
Because that one has the Fe2 plus has more electrons, it's going to be larger.
Yes, it is. Fe2 plus will be larger. So does Fe2 plus have more energy levels? Because remember, we talked about size. There's really two reasons why the size would change. It's not because it has more energy levels. What, Nick?
There's fewer repulsions.
Yes. Yes. Okay, so the number of electrons. Okay, so we have Fe plus 4 has more electrons. That means more electron repulsions, which take up more space. Oops, it's not Fe plus 4, it's Fe plus 2. Fe plus 2. Okay. How are we doing? I'm going to throw a couple at you and see how you handle them, okay? So I'm going to go back up to where I added the page where there's more space. And I want you to kind of figure out which one is larger or smaller and why, okay? So we'll do 3 examples. Okay. All you're not done, that's okay. Let's start talking about this though. So for number 1, got sulfur with a -2 charge versus argon. Who's got a guess? Yeah.
Argon?
Is what? Is larger or smaller?
Small.
I agree. Argon is smaller. Why is that?
Has more protons and the same number of electrons.
Okay, yep. So in any kind of comparison question, that's kind of the first place you want to start, is you want to start with your proton and electron count, right? So argon has 18 protons, sulfur has 16 protons, argon has 18 electrons, sulfur also has 18 electrons. So you must address the difference, and the difference here is the number of protons. So argon is smaller, it has more protons, attracting the electrons more strongly, reducing size. Okay. How about the second one? Yeah, too.
Chlorine with the neutral charge
Is what? Bigger or smaller?
is smaller because when it has a negative charge, it has more electrons and more repulsion.
Yes. Okay, so chlorine, see they both have 17 protons. 17 electrons versus 18 electrons. More electrons means more repulsions. The charge is constant, so the charge is not up for discussion. So, okay. Third example. Ben?
Phosphorus with a +2 charge is smaller.
Yes. Explain.
It has less electrons and smaller repulsion.
Okay. Same number of protons, fewer electrons. All right, so fewer electrons, less repulsion, smaller size. Okay, let me just throw one more at you. Selenium versus tellurium. Neither one of these is an ion. These are just straight up atoms. So which one is bigger or smaller, and why? Edgar, what do you think?
Chlorine is bigger because it has more energy levels.
Yes. Yeah. So this is not, we're not thinking the same way as we did with the other ones. This is from yesterday, right? So simply more energy levels. Okay. All right. So the second topic for today is what we call ionization energy. You're somewhat familiar with this because you did graph it. You had to look up the definition. So it's the energy needed to remove an electron. Technically speaking, we're removing an electron from an isolated gaseous atom, but that extra stuff is not really where we need to focus. It's just essentially the energy needed to remove an electron, right? And it's also a measure of how tightly the electrons are held. So, the trend for ionization energy, it increases from top to bottom. Okay, so increases from top to bottom. All right, so that means in a family, oops, no, I'm sorry, I said that backwards. I got that reversed. From bottom to top. Right, so the larger family members have low ionization energy. The smaller ones have high ionization energy. Let's think about why that would be. If you're trying to remove an electron and pull one away, you've got to consider how close is that electron to the nucleus. Because the closer the electron is to the nucleus, the more strongly the electron is attracted. So small atoms means electron is closer to the nucleus, which means stronger attraction, which means it requires more energy to pull one off. And vice versa with the large one. The larger atoms, the electron is pretty far away, it's not attracted as much. It's going to have a low ionization energy because they're larger. Okay, so that addresses the vertical trend. Let's talk about the horizontal trend. Ionization energy increases from left to right. Now, based on that logic and what we just discussed, hopefully that makes sense. Because what's happening when you go from left to right? From left to right? Yeah, it's getting smaller. And we know the reason why it gets smaller is because of something called effective nuclear charge. So from left to right, the ionization energy increases because on the right side you have higher effective nuclear charge. And effective nuclear charge is the strength of attraction between the nucleus and the electrons. So of course it's going to be more difficult to remove an electron when that electron is attracted very strongly. Okay? All right, so from your lab, when we looked at the alkali metals, both in the demonstration and the video, the most reactive one they shown was cesium. Technically, francium is the most reactive, but there's not enough francium to really experiment with, right? But you actually saw them react cesium, and that's the one that exploded the glass bowl, right? The lithium was just a little fizzing. It was reactive, but it was the least reactive. So lithium is the least reactive of the alkali metals. Cesium is the most. What's the reason? Well, what do you know about a family now that you know what ionization energy is? So does cesium have the most or the least ionization energy in the family? The least. Cesium requires the smallest amount of energy to react. So that's why it reacted the most, because the water temperature was constant in every trial. Nobody was boiling water, nobody was cooling water. The water was just tap water in every instance, right? So room temperature water. But because the energy requirements to react got lower and lower and lower for the bigger atoms, it was just easier for them to react, and that's why they reacted fast. All right. Conversely, nonmetals gain electrons, all right? And the trend is opposite for reactivity. So more reactive means gain electrons easily. Fluorine is the best. Fluorine is the most reactive nonmetal. What do we know about fluorine? Well, it's got very high effective nuclear charge. It's small and has high ionization energy. What about the last column, the noble gases? How come I didn't say helium or neon are the most reactive nonmetals? What do you know about them? The noble gases. They're unreactive. That's why we're ignoring them. Okay, so nonmetals gain electrons. Which are the ones that are good at gaining electrons? The ones with high effective nuclear charge and are small. So that means like these guys here. These are like the most reactive nonmetals. And to a lesser extent, this guy. Okay? But you have to remember, nonmetals gain the electrons, the metals lose the electrons. They behave oppositely. Okay. So the last thing then to talk about is this concept of successive ionization energies. And this one can be kind of confusing, so I'll try to go slow. We talked about sodium before. And we said how sodium was 1s2, 2s2, 2p6, 3s1. And we went through and we identified the valence electrons and we identified the core electrons, right? So if sodium becomes an ion, it does so by losing an electron. When sodium loses the 3s1 electron, that's when it becomes an ion. Now here's the thing that you should remember. Only valence electrons can be removed. All right, that's very important. You can only remove the valence electrons. So, having said that, let's look at this chart here. This chart shows us the ionization energy cost. And right now we're talking about sodium. So here's sodium, and the amount of energy it takes. So these are listings of ionization energies. This first row is the first electron to be removed. So removing one electron from sodium costs 496 kilojoules. That sounds like a lot, but compare this to this. This is the second ionization energy, and it's like almost 10 times the amount of the first. So what that tells you is that one electron can be removed, but the second one is virtually impossible to remove, so it's not going to happen. Okay? Let's look at magnesium. Magnesium, 1s2, 2s2, 2p6, 3s2. Magnesium has 2 valence electrons. So magnesium, when we look at the chart, the amount of energy to remove one electron, 738 kilojoules. Again, that sounds like a lot. Oh, look, this value is more than sodium's. I wonder why magnesium has a higher ionization energy than sodium. Can someone give me a reason? It goes back to the first trend. The first trend we mentioned was the most important one. Not the first trend today, but the first trend last class. The one with the acronym. 3-letter acronym. Starts with a C. E. Ends with a C. Yeah, the effective nuclear charge. Right? Doesn't magnesium have greater effective nuclear charge than sodium? Yes, Mr. Park, it does. Oh, this makes so much sense that costs more energy to take an electron away from magnesium. But now, if we just look at magnesium, the second electron, if I wanted to remove a second electron from magnesium, it's going to cost twice as much as the first. And you might think, oh man, that's a huge markup, right? But look at this jump. 1,400 to 7,700, that's a huge change. That huge change tells you 2 electrons can be removed, but not 3. This will happen, but not this. All right, maybe drawing a picture will help. So here's the nucleus. Here's energy level 1. Here's energy level 2. Here's energy level 3. Look at the distance between the nucleus and the electrons. When I try to remove an electron from energy level 3, it's a lot farther. It makes sense that it's easier to remove the ones that are farther. But after I've pulled off the 2 valence electrons here, right, after I've pulled off these guys right here, and now I want to try to reach into the 2p subshell, that's not happening because the energy level 2 is so much closer than energy level 3. Case in point, you cannot remove core electrons, only valence electrons. Right? So aluminum has 3 valence electrons. You can clearly tell because 500, 1800, 2700, 11,000, this gigantic jump right here from these two. After you've pulled off 3 electrons, the 4th electron would be coming from the core. It won't be removed. Is this making sense, guys? Yeah, question.
Is it like physically impossible to remove that electron?
Oh, okay, so good question. So when I say it's not going to happen, what I mean is it's not going to happen naturally. There are ways to forcibly remove electrons from atoms, but you need a particle accelerator, which, you know, I keep mine in the drawer back there, you know, because kids like to fiddle with it. There's very few of those in the world, right? Okay, so let me give you some numbers here. I want you to tell me how many valence electrons you think this element has. And I'm going to do that by giving you a list of ionization energies. So I'm trying to find some space here. Here, we'll go here. Okay, so ionization energy 1, IE2, IE3, IE4, IE5, IE6. Okay. I took an element and I removed 6 electrons from it. Based on how much energy it took to remove each of those, how many valence electrons did this element have? Nate? 4. Yes. The biggest jump happened here. You were able to pull 4 off, but the 5th one was much, much more. Maybe I didn't make those numbers as dramatic, but the point is you're looking for whatever the biggest change is. And that's a sign of how many valence electrons were removed. Okay. How are we doing? Okay. All right. Then that's enough of that for today.